Hello, so I'm going to do a series of small little examples and lecture notes. Instead of having one big long file, I'll cut it down in pieces. This is to make up for the day we're losing due to snow, or at least the lecture time we're losing due to snow. I'm going to pick up from where we left off, which we were just beginning to talk about problem 52. So I'll pull up 52 here. It's this problem here. And they were stating Jay and Morgan work in the summer for a landscaper. It takes Jay 3 hours to complete the company's largest yard alone. Morgan helps him. It takes only 1 hour. How much time would it take Morgan alone? So I'm going to want to record information for what's happening with Jay and Morgan. One of the things we'll want to do with this, we'll want to look at it as a rate. We want to use our units to help us lay out what's happening. One of the things that the books tend to do with equations like this or systems like this is they drop the units because the ratios that come out of them are fairly predictable. We're going to look at the units right now to help it guide us in how we're going to do this problem. And so Jay is doing get the right pen here, one job. I'll bring that JB in 3 hours. And so this is a way of talking about the rate Jay is doing work. And again, as we progress, we'll see rates are very special in linear equations. We will tie rates to slopes. So Morgan they finish one job in X hours. And together, we get one job in 1 hour. Rates are additive. We will see this with velocities. We'll see it with information flow. Rates add on top of each other. If you were moving at one rate and you like in a wind, and you try to accelerate in that, you add the two rates. And so in the case of Jay and Morgan, their rates are adding together to give the total rate in which they finish the work. And so here is Jay's rate, Morgan's rate, and their rate together. Now, this is fractional with our variable in the denominator, but we can take our common denominator. So we have in the bottom of this fraction here, 3 hours. In the bottom of this fraction here, X hours. And we have 1 hour here. So I'm going to multiply this entire system by 3 hours times X hours. Now notice for right now I'm keeping the unit. As we do more of these, we just need to be aware of our units and we can attach them on at the end. For right now I'm keeping our unit. Now I'm writing this notation with parentheses. What this is letting me do is I multiply this to both sides of the equation. I can distribute it across an equation. It's a way of saying whatever I do to one side, I do to the other. What I'm going to be doing to one side is multiplying 3 hours times X hours. So I'm going to distribute this to the first term, to the second term, and the third term across the equal sign. So I have 3 multiplications. When I multiply hours by hours, one of these units will cancel, and the 3's cancel. Actually, give me a second here. I'm going to use blue because that's the color of that arrow. So the hours cancel an hours here, and the 3 cancels the 3 here. So I'm left with an x hours times 1 job. X hours times 1 job. And so over here, when I go across my green path here, the hours cancel, one of the hours cancels, and the x cancels. So I'm left with a 3 hours job. And finally, when I come across to the other side of the equal sign, an hours cancels, but the 3 and the x are still there. So I get 3x job. Well, every term has a job in it. So if I divide the right-hand side by job, that will cancel. But if I divide the right-hand side by job, I have to do the same thing on the left-hand side. So the left-hand side cancels. And so I get x in hours plus 3 in hours equals 3x hours. Ran out of space, forgot to write the hours there, but we're good. Okay, so I will collect like terms. Pull this up to the top here. And subtracting x from each side, I get 2x equals 3. Or x equals 3/2. Putting this in terms of our original problem, Morgan takes 1.5 hours to do the job. Most textbooks ignore the units and they immediately write the ratios. So you'll see this example done as J does 1 job in 3 hours. Morgan does 1 job in X hours. Together, they do 1 job in 1 hour. These combine for 1/3 plus 1 over X equals 1 over 1. I actually prefer this way of writing it, but I use the units to show why we created these fractions. And at this point, our common denominator is 3x, so I get x. I'll multiply everything by 3x. I'll get x plus 3 equals 3x, and this solves the same. And so you'll have a tendency to talk to it without the units in there. I wanted to highlight the units to see why we chose the fractions and why we get the variable in the bottom of the fraction. I would look at the examples in the book and work on the work problems. And these work with work. They also work with flow rates. We'll see some things later on where we do liquid flowing in to a container, and it takes one pipe X hours to empty a tank and another pipe 2 hours to empty a tank. If you open both pipes at the same time, together the tank empties in an hour. How long did the other pipe take? It's the same idea where you have a fraction of the work being done by individual objects and they combine. And we'll see more examples as we progress. This comes up in successive chapters. We'll see it again in chapter 2, 3, and 4, where we're combining rates of things that aren't specifically stated in rates. I'm going to stop this video here with this example, and I'm going to have another one where we will look at, like I said, we're going to look at examples of applications in 1.2. So we're going to do about 3 examples in 1.2, and then we're going to look at some stuff from 1.3.